By okay. So, okay, perfect. Did you have any like maths lectures? Yeah. Okay. Well, but we'll start slowly. I'll actually quickly recap what we've done last time. So, like in a fast pace. So, well, we talked about why we want to do probabilistic modeling. Well, so usually we observe some data and want to do some inferences on them, and data are uncertain. And well, we talked a lot about probability theory, and yeah, I mean, all these methods are also applicable to non-biological applications, but we'll focus on biological ones in this course. Well, why do we want to do probabilistic modeling? We said, for example, if we have expression values for two genes and measure their correlation in form of such a regression curve, then, well, we can answer several questions. We can basically say, okay, there seems to be some correlation. We can predict new values, but we can also do other things, but wrong. We can do other things wrong. For example, if we don't use all the data that is available, for example, knowledge about these two sets of samples have been measured in different conditions or something like that. So we always want to use all our data, and we'll talk about methods for that. And also, if there is something that is not measured but that influences all our data, we'll see methods on how this will work. Yeah, genome-wide association studies. We said measure associations between traits and genetics. Okay, so this is kind of these nodes are random variables. Edges are dependencies between the random variables. If they are solid, then there is a direct dependence. If they're not solid, then not. And in this case, the dependence would go via z. This might be a measured gene, and this might be a measured phenotype, and then we want to answer the question whether the gene regulates the phenotype or not. Well, some further material. Oh, maybe this is interesting for you. So, well, most of the course will be linear methods. They are basically the founding for everything else. So it's kind of linear regressions and generalizations and latent variable models, like principal components analysis is something that you might know. And later we'll talk about kernel methods. So kernel methods basically are a way to make all these linear models non-linear in a very principled and elegant way. Well, probabilities are there to describe an experiment, where we basically say, well, we have some experimental setup, and if we observe the outcome of the experiment and do that for every possible outcome, we can assign a probability to each of those outcomes. Well, there were some rules for calculation with probabilities. For example, we can talk about for two events. So this is basically the whole space of events is omega, and for two events that are subsets of omegas, there are ways to, for example, compute the union of these two. If the two events don't overlap, then the probability of observing the union is the probability of the sum, and the probability of the intersection is 0 because they don't intersect. And if you take the sum over all possible events that are disjoint, then the probabilities will sum to 1. So we have intersections, unions. In general, these might overlap. So this is what we've seen so far for the non-overlapping one. But in this case, if they overlap, this was here for the union. if they overlap, then basically we're double counting this part. We have to subtract it, and in this case, well, it's just the other way around here. Well, the complement of an event is the rest, and together, of course, the probability sum to 1. Well, an event can be a subset of a different event, in which case, well, their probabilities are very related by these rules. We can combine events, for example, by performing the same event several times, or by measuring basically performing different experiments that are somehow related to each other, like measuring multiple genes in the same individual. And these can be independent or dependent. And well, conditional probability is basically a way to relate the probabilities of two events if we know the outcome of one. Well, there are many cases, for example, if one event is a subset of another one, so basically whenever we observe this event, then we'll also observe the superset, then knowing that A happens will tell us that also B happens and things like that. And the rules to compute this conditional probability, so this is the probability that A happen, given that we already observed that B happens, is well, the probability of the intersection, so the probability that happens. And now we already know that B happens, so we are already somewhere in this circle, so we only have to divide or normalize by the area of this event B. And well, there's also the product rule, which can be derived from this. So these two rules are very important. The product rule gives us a way to write down the joint distributions from the conditional distribution and the marginal distribution of the other event. There's the notion of independence. If there's two events are independent, then basically the joint distribution factorizes. So it's the product of the two marginal distributions. Random variables are basically a way to, it's just basically defining variables from events, variables of interest. And well, they have a set of possible values. For example, the number of orange balls that we pick out of these things to things in n trials is a natural number. Or the number of heads that we flip with a coin before we flip the first tails is also a natural number. Well, the gene expression of time t is an example of an event that is from real number, and for example, the average gene expression, that's an example of a combination of. So basically, we could write down the probability of a single gene expression measurement, but we can also write down the probability of the average. So this is kind of taking some experiment that consists of multiple experiments and lumping things together and into a single random variable. Well, probability distributions are either discrete, in which case we call it the probability distribution and probability mass functions, and in the continuous case, it's a density function. So they're all non-negative, both of them. The probability mass functions, all the values are smaller than 1. For the density, they can be larger than 1. The only deal is that they have to, in the discrete case, sum to 1. And because it's a sum, they have to be all smaller than 1, or smaller or equal to 1. But in the continuous case, the summation is replaced by an integral. So an integral is basically, well, if we integrate from a to b, then we basically get the area under this curve between a and b, which equals the probability. Now this is a discrete thing. The probability that we observe the random variable between a and b, and that is now a number. that is smaller than 1. Well, the expected value is the average value of a random variable, and we can compute an estimate of it from some data. So by just computing the sample mean or the average of them, and it's the first moment of a distribution of a random variable, and well, there's a discrete case and a continuous case. It's just a discrete case, it's a weighted average over all the possible values of x times the probability, and then in the continuous case, it's the integral, the variance. It's now the average squared difference from the mean, so to say. It's a second centralized moment of the random variable, and it's a square of the so-called standard deviation. Yeah, I mean, in the discrete case, this is just, again, a weighted sum over the squared difference to the mean, in this case to the expectation. In the continuous case, it's, we just, again, replace the sum by integration, and then we get the same thing. Yeah, so again, the sum rule and the product rule are very important. We can use them to manipulate probabilities. Information and entropy. This is, I put in some more material on this today because I was not very happy with the material last time. So information measures reduction in uncertainty about a variable. So basically the entropy is a quantitative description of uncertainty, in the sense, it's kind of, think of entropy of a random variable, the number of bits that you need to write down the complete distribution over the random variable. And if you know the exact value, then this is 0, right? I mean, if you know it, you don't need to write down anything. And it's, of course, maximal if all possibilities of, so all possible values of x are equally probable. And yeah, so this is the type of function that we're looking for, and the function is the entropy function. And it's this, again, this average minus log p of x taking a value weighted by the value of x, by the probability of the value of x. And, well, the entropy is a vector valued function, which means that the input is not, we don't compute the entropy of a single value of x, but of the whole probability distribution. So think of the input as all values with assigned probabilities. So, right? And this will also answer one of the questions that came up last week. And here's an example for the binary entropy function. So this is now the random variable x just can take two values, either 0 or 1. And well, given now this basically, if you have two values, the probability of observing the other is just 1 minus the probability of observing the first. So we only need actually just one input to describe it, because the other one is deterministic. And we see that the entropy, if the probability of observing x, value of x is 0, then the probability of observing the other value is 1. So the entropy is 0, because we're absolutely certain about the value, and the same on the other side. And the entropy is maximized if the probability of both occurrences is equal. Think of entropy as the average surprise of finding out that the value of x is x. And we talked about the conditional entropy. Well, last time we talked about the conditional of entropy of x given the distribution of y. Here we look at a single value. For that reason, it's it's basically an average, well, of the kind of the average of surprise of observing x when we know that y has the value y. So it's only a single value of y, but we sum over x. Now, this is what we saw last time. That's the conditional entropy of x given the random variable y. Now, y has a probability distribution. It's not just a single, value, and for that reason, it's kind of the now it's not just the entropy of x given the value y, but it's the average over the probability distribution of y. If we knew that value for every possible value, what would it tell us about x? What would be the entropy of x for given y would be that value for every value? For that reason, it's a double sum. So that's the average, and then we have the formula that we had last time, where we have this sum over the two random variables. Right?
So when you say the number of bits that we need to encode the distribution, we need to write down the distribution, what exactly do we encode by then? I mean, what do you need to write down?
Well, now we would have to get kind of into this like noisy channel communication thing.
Yeah.
So say you're sitting somewhere and you're sending out the distribution over. You basically want to say, I've got this bits of information here, which is my random variable. It can have certain states, and I want to transmit its value. Now, if think of the distribution as, well, maximizing the entropy is kind of okay. So if there's only one possible value, then I don't need to transmit anything. So that's the number of bits. So you're first installing kind of the decoder on the other side. So you don't need to send anything. Well, if beforehand two possible values are equally probable, then you have to say, or if basically two values are equally probable, then you have to give the probabilities of both. And, yeah. I'm not an expert on this. But this is related to compression. So if you have a matrix and the more random, for example, a matrix of values, think of you have just a string of zeros and ones. If you randomly observe ones and zeros at the same probability, then it's harder to encode that if you know that a certain fraction of the values are zeros. If it's a very large number of zeros, then you only can basically, for example, submit only the few ones and forget the rest. And kind of the entropy tells you what would be the optimal theoretical number of bits that you would have to send. Okay, so the chain rule. So it's the joint entropy of x and y. I mean, again, x and y together have a joint probability distribution. Given by the entropy of x and the conditional entropy of x, which is the same as the other way around, so that is symmetric. The mutual information is now defined as the entropy of x minus the entropy of x given y, so, and which is the same as well the joint, basically the entropy of the individual variables minus their joint entropy, and for that reason it's symmetric. And think of the mutual information as the average reduction in uncertainty about x when learning the value of y, and vice versa. So if you had, if you want to learn the distribution over y, and you could choose, well, you have x and y have a joint distribution. You want to learn, you're actually interested in learning the distribution of y. But you can, you always observe pairs of them, and now you can choose your optimal x such that it would tell you most about y, and then you would choose the one that maximizes mutual information.
In the chain rule, how come that first part you add them, but the second part you subtract them?
That's a typo.
So is it subtracting or adding?
It's adding. Adding. Yeah. And yeah, all these quantities relate to each other. So so we have the joint entropy over both variables, which basically means we have to encode both variables with all their possible values. There's the entropy of x. It overlaps with the entropy of y. There's the mutual information. And yeah, that's basically the two conditional entropies plus the mutual information add up to the joint entropy, which follows also from all these quantities here. Okay. Well, under independence, x and y, the probability distributions of x and y factorize, and also the joint entropy in this case is the sum of the entropies. Well, the joint entropy. Well, let's prove that. So the joint entropy is now it's what we said. It's the sum over all the values of the joint probability, and the joint probability factorizes times the log of the joint probability. Again, the joint probability factorizes. Well, now we can the log of the product of the log of a product is a sum, so we can now split these things up. So move x here, move y here, to sum over all these things. And now if we sum over x, then basically what will happen here is that this is kind of now an think of this now. I mean, this is basically now an expectation over x, if we sum over x, of p of y times log y, log p of y, right? But if we the expectation over something that does not contain x will just be that quantity because we take the average of all the possible values and these sum to 1, the probability. So on this side, the sum over x just goes away. The same thing will happen when we sum over y on this side. Right, and we just get the sum over the two entropies. Yeah, also the mutual information is 0 because the joint entropy is the sum over the two entropies, and so basically we just subtract the same thing again. And of course, the conditional entropy is just the entropy of x. Questions to this?
Technically, what kind of entropy will applicate to mathematics problem?
I'm not sure yet, but think of, okay, I mean, entropy, well, or mutual information, for example, tells us exactly what I said. If you could, for example, choose a measurement. Say you have an experiment, you want to learn something about well, I have to construct something now. Say you want to learn all the kind of the natural variation of of a plant, right? I mean, you want to describe its some phenotype about it, the height, and you're given the genetics. And sometimes measuring a phenotype, for example, is expensive. So you want to do as few measurements as possible, but you have a database of all the measured genotypes because they have been sequenced somewhere else or chipped somewhere else. So you're given, you know X. X is the genotype for all of these because they have been done before. Now the question is, how do I select as few individuals or as few genotypes as possible to learn as much as possible about the phenotype? Which, if the phenotype depends on the genotype, then the mutual information, or the expected reduction in entropy would be such a selection criterion, right? So.
There was an example when I was doing RNA-seq. Someone wanted to know if the way the reads map, for example, to the genome are randomly distributed or not. You can just from measuring like how many reads are mapped to each position, you can figure out sort of distribution and the probabilities from that. And from that, you can measure entropy to see if there's something else going on or if it is truly random. Because the higher the entropy, of course, the more random it is. So then you can set some sort of threshold and say below this threshold, we're going to look more closely at what's happening here. Maybe there's some binding factors. Another example.
Very good. Interesting example. Right. So any more questions? I mean, basically, the methods are all there. Most of them are very old, well developed. Not all of them are right now regularly applied in bioinformatics, but the important bit to learn is that these methods are very general, and if you find a problem in bioinformatics where this would fit in, we've seen now 2 possible problems, then why not try it out? Okay, so this is just the proof for this. I mean, proof is pretty simple. We've seen this, so we won't do it again. And I've now added and tell if it's lighter or heavier, so it is possible. In 3. In 3. Okay, so the Kullback-Leibler divergence. That's another application of entropy in bioinformatics, because we will use the Kullback-Leibler divergence definitely for constructing inference algorithms. So the Kullback-Leibler divergence, basically for 2 probability distributions over X, so it's 2 distributions over the same variable in this case, P of X and Q of X. The Kell divergence is defined as the average, it's defined as this. How can we say it's it's kind of an expectation of the difference in the log probabilities. You can write this out as a difference because it's a quote. How do you call it? Quotient of two values becomes a difference. It's not symmetric, so the Kell divergence between P and Q is not the same as the Kell divergence between Q and P. It's a strictly convex function. So here's a definition of convexity. Convexity is something very useful. It's basically a function is convex over an interval AB. So in this case, the interval AB, I would say, is minus infinite to plus infinite, for example. If for every 2 values in that interval, And for a value of lambda, which is smaller than between 0 and 1, the function of, well, their weighted average weighted by lambda is smaller than the function of basically the weighted average of the two functions weighted by lambda. So if we write down the function, for example, it means that, well, if this point is the weighted average, x star is the weighted average of x1 and x2. If I evaluate the function, I will always get a smaller value than if I take the weighted average of the two functions. So the function will always be below these averages of the functions. Is this concept clear?
Yeah, doing for the definition, it should be q of x, not y.
Yes. Yes.
What exactly are you trying to say when you say two probability distribution functions, two probability distributions over x? What does that mean?
Well, say, okay, so say I have a true probability distribution, but I cannot really write it down because it's complicated, or I don't know it. Now I can choose a simpler one. For example, I have a non-Gaussian distributed random variable, and I want to approximate it by a Gaussian. Then the KL divergence gives me a distance between these two distributions, between the true and my approximation family. So it gives me a recipe how to choose a good approximation. For example, I could minimize the KL divergence between these two.
It also tells you how much you would lose of information if you approximate P with Q.
Right.
Right. So, I mean, you're always doing it.
So it gives you two things. It basically gives you a recipe, a scoring function, but it also tells you what's the difference. The KL divergence is always larger or equal to 0. It's something that's called Gibbs inequality. And it follows from convexity. And that it's minimized at 0 if and only if P equals Q. So KL divergence is only 0 if the two probability distributions is the same. Otherwise, there will always be a loss in information. That's what it means. Only the true information, the true probability distributions give me all the information. Yeah, that's what I already said. This will be lost in space for a while, but we'll use it later in this class. When we come to inference problems where we cannot just estimating the mean of a normal distribution was very easy last time, but there will be distributions where it's not that easy. And then this tells us how to approximate, as I said, a complicated distribution with a simpler one. Okay, so, well, the normal distribution, there we are, has a data-dependent term, which is the squared distance to the mean. And, well, because it has to be normalized, if we basically take the integral over this, then the integral over this is equal to square root over 2 pi sigma squared, so it's normalized now. And there's a multivariate normal distribution. In the multivariate normal distribution, all the constants are replaced by vectors except for the variance. The variance is now a matrix. It's a so-called covariance matrix. but the terms look very analogous. So basically we have now, instead of a sum of squares, we have a squared form. So this is basically also just, think of it just as a square for vectors. And yeah, the normalizing constant now contains the determinant of the covariance instead of just the variance. Well, other probability distributions. I actually looked up whether there's an easy sampling process that would yield a gamma distribution. I didn't find something. It's a useful distribution, we'll need it. And it is, well, as I said, it's the continuous extension of the negative binomial distribution. The negative binomial distribution is the distribution that you would get if you would flip a coin unless, and would count, for example, the occurrences of heads until you observe a given number of tails. And well, has this funny shape. Only takes positive values, the gamma distribution. So x is always larger than 0. Well, the normal distribution, again, the moments of the normal distribution, so its expectation, this is just a different notation, is equal to the mean, and the variance is equal well, to the variance. That's why they have these names. Well, so far we always use probabilities to describe probability distributions to describe events. We wrote down our probability or experiments. We wrote down the probability distribution. Said, okay, now if we flip a coin n times, what happens? But with this probability, what's the distribution? But we don't know usually the parameters. We don't know the probability of heads or tails. So we want to learn it from data. We just have observations, and then we want to go back to find the parameters. And we do that by using the probability of the data given the parameters. And we use this, think of this probability of the data given the parameters as writing down a hypothesis, because we have to choose a form of this. We have to choose a parameterization. And think of this, which we call the likelihood, the probability of the data given the parameters, as a scoring functions for the parameters. The data is fixed. We have it in our computer. It's observed. Now, the question is, what is the distribution that generated this data? We don't know it. We want to estimate it. For example, we need a model. The model gives us this P of the data given the parameters. For example, a Gaussian. And well, if we write down this distribution for all the observations, then this is the likelihood. As I said, the likelihood is a scoring function for the parameter. So don't say the likelihood of the data, it's the likelihood of the parameters given the data. Or it's the likelihood of the data given the parameters, but if you don't say just likelihood of the data, it's the likelihood of the parameters. So maximizing this likelihood is a way to choose those parameters, and it's a good one. It has a lot of nice properties. So for the normal distribution, we did this last week. We saw that well, maximizing the likelihood is the same as maximizing the log likelihood. Usually, this is mathematically a little bit simpler. That's why we use the log likelihood. And if we maximize this, then we get the sample mean as the maximum likelihood parameter for the mean, and the sample variance as the maximum likelihood parameter for the variance. Well, they're equivalent to the mean and variance that we typically write down for data, so these sample estimates. But, well, they also have problems because maximum likelihood just gives us one parameter, just one estimate, and says this is it. It does not quantify, well, there's some uncertainty here, so that's hard to do. And the way to quantify this uncertainty is Bayesian inference. Well, we use the sum and the product rule that we've seen before to write down Bayes' theorem. So now we're actually starting new material. So now, given the conditional distribution of x times y, if we know this quantity and we know the distribution of y, then we can use Bayes' theorem to get the conditional distribution in the other direction. That's why Bayes' theorem is also well, this conditional distribution is also often called reverse probability. Or no, this conditional distribution is often called reverse probability. Think of the likelihood as a forward probability. It's a distribution of the data, so it's kind of a generative mechanism. And given this generative mechanism of data and observing it, and the prior over the parameters, we can infer a distribution over the possible parameters. That is Bayesian. That is all that Bayesian inference does. Bayesian inference is often very costly because it involves computing this normalizing constant here, so P of data, which is, well, it's just taking the joint distribution over the data and the parameter and summing out the parameter. So there's in the continuous case, an integral. And, well, this is just the joint distribution is just the top term. So it's the likelihood times the prior and integrated over the parameter, which just means what is the average likelihood or the average probability of the data taking all possible values of the parameter into account. So not just one, but all possible values. They're weighted by the prior. The prior is kind of our a priori belief what probabilities of possible parameter values would be. So our recipe to get the posterior is we define a likelihood. So for example, a Gaussian distribution. We want to estimate the parameters of the Gaussian distribution. Then we define a prior over those parameters, and then we just apply these rules. It's from a mathematical standpoint, simple and elegant. Often in practice, it's very hard because it involves this integral. So let's use this for the normal distribution. Actually, let's do something a little bit simpler. But let's do the first thing. So our likelihood, we assume that the data is normally distributed. That is already an assumption. In Bayesian inference, you always write down all your assumptions. You write down what you think your data looks like, what's the class of distributions, and you think what your parameter could look like. So you specify a prior over the parameter, In this case, we assume that the variance is known. And then we get something, well, we just take the product over the two. This doesn't give us yet the posterior, but it's only something that is proportional to it, because it misses this normalizing constant here. So, but if we say we want to do only a first step, say we want to use the Bayesian approach only to get a single estimate of the parameter. Now, if we vary the parameter doesn't appear in this normalizing constant. If we vary the parameter, then only this part varies. So if that part is maximized with respect to the parameter, then it's also maximized in the posterior. So, well, this sort of what I just described is maximum a posteriori estimation. It's kind of a mishmash between well, the frequentist approach of maximum likelihood and the Bayesian approach, where you specify a prior, but then you just get a single estimate. Well, then let's do that now for the mean of the Gaussian. So we write down this distribution, which is it's actually the joint distribution over the parameter and the data. And as I said, this is proportional to the posterior. Take the log of that. Now, that's a simple trick. We put it equals here, and we just say everything else is a constant. It doesn't contain anything that we're interested in, so we just pull it into a constant. Well, plugging in the formulas, we see that we have something that is now square in the data, so it measures the square difference of the data and the parameter, but it also measures the square difference of the parameter to its mean, where the mean is the prior mean. It's what we assume the mean would be. If we don't know it, then usually that is a 0. And now, well, just rearranging the thing, pulling again everything that does not depend on the data and on the parameter into the constant, we're left with that. And that is the only part that we have to maximize now, because this part won't do a thing. We again take a derivative. What's the derivative? This time well, it's down there again. It's always a useful exercise to just take derivatives quickly with respect to the parameter. So if you take the derivative of this, well, 2 times that, 2 times that part, and we have to take the derivative of the inside, which is just -1. And then we basically get this part. The same thing there. Now we set this to 0. And, well, set this to 0. Now, what we want is the parameter, so we put everything on the one side that doesn't belong to the parameter. And solve. And now what we see is that, well, remember the maximum likelihood estimate. The maximum likelihood estimate was the sample mean, was 1 over n times xn. Now we have kind of a, well, it's again a mean, but it's now a weighted average. It's a weighted average between the sample mean and the prior mean of the parameter. And how is it weighted as delta? Well, delta is just a ratio of the data variance and the prior variance of the mean. And well, think of this part being 0. Right? If this is 0, then this whole thing becomes 0. In which case, delta could be thought of as a shrinkage parameter. In general, it's a regularization parameter. It's this part. Well, m0 is always the same. That's our prior. So that's kind of the constant that we plug in. This part depends on the data. It's the maximum likelihood estimate. And if you change the data, this can change a lot. So we kind of regularize the way that this parameter can move compared to the maximum likelihood estimator. Is that clear? Yeah? M0 is the prior mean. So it's the remember that the prior of a mu was a normal distribution, and well, this is the mean of this normal distribution. So it's the maximum a posteriori estimate is a weighted average between the mean of the prior distribution and this mu hat is the maximum likelihood estimator. So it's between those two.
So did you just do this once? And then how do you know if your prior estimate was anywhere close? Like, if this seems dependent along your prior estimate?
Yes.
Okay.
Right. Well.
So we're just trading off the uncertainty in the maximum likelihood where our sample size could be really small or whatever, or maybe uncertainty in whether our prior is any good.
That's exactly right. But I mean, there are ways to construct priors that are highly flexible. For example, I mean, if you already have a lot of knowledge about how the distribution should look like, then well, you can write down a very informative prior. But if you don't know how the parameter would look like, then you can make your prior distribution really broad. For example, give it a variance that goes to infinite. If the variance goes to infinite, then basically, well, this ratio, this parameter becomes 0, and we are left with a maximum likelihood estimate. Or make it very large, the variance of that. So the larger the variance of the prior, the closer you are to the maximum likelihood estimator in this case. The more, again, this parameter can move. So, yes, I mean, it's a criticism about Bayesianism that it always creates bias. You always put in your beliefs. If your beliefs are wrong, then your estimate will be wrong. But on the other side, even frequentist estimation, there is a lot of assumptions there. They're just often a little bit hidden. For example, I mean, there's already the assumption that the data is normally distributed. Who tells me that? If the data is not normally distributed, the estimate will also be garbage, right? Bayesian statistics is a way to write down all your assumptions. You write down the likelihood, you write down your prior, the rest just follows from that. It's all written down. There's no hidden information anywhere. Okay, that was Bayesian estimation, which is maximum likelihood estimation. Now we come to full Bayesian inference. As I said, in reality, we want to estimate the whole posterior distribution. Again, we have our data. We write down our model, which is, again, this normal distribution and the likelihood, same as before. And combine it with, again, the same prior. Now, the posterior is proportional to this. As I said, we need a normalized distribution in the end. So this is not enough. This will not be enough. But let's go only with the joint for now. So let's write down the joint distribution, which will be proportional to the posterior distribution. Well, this is the likelihood. So it's the product over all those Gaussians, and this is the prior. If we rearrange those, we get this part. Now, the interesting bit is, well, I mean, all those constants, we're already just proportional, so let's get rid of those as well. Let's only concentrate on that part, which is this part here and this part here. So this is the e to the power, the exponential function. Well, we know that our distribution, our posterior distribution, is a distribution over mu. Right? That's what this says. So we need to concentrate on everything that contains mu. And, well, if you look at this, mu always appears kind of as a square here. This kind of gives us an idea how the posterior distribution could look like. Any ideas? Well, we've seen. Do you know distributions that are related to the squares of the variable that? I mean, so we have this e here. How about the Gaussian? Okay, so let's try to put this into a Gaussian form. Let's try to take all these things and just complete the squares. You know completing the squares? So you bring it into a form that here has everything, that basically has the square of this thing here, and 2 times this times something and a constant. Right? And, well, we know that if you take the Gaussian, we have this e to the minus 1 over 2 sigma squared x minus mu is now a little bit this mu and let's write it like this. We have mu minus the mean of mu squared. Well, this is just it's proportional to, right? The normal. Minus 1 over 2 sigma squared. Mu squared minus 2 mu, the mean of mu, minus something. But we know, well, which is, the something is very easy, it's just 2. Right? But from this form, we can just read off, if we bring it into this form, then we can just read off the mean. Because this part, if you bring it into this, write down some constant. I mean, it's already not not normalize the whole distribution. And the whole bit here does not depend on mu. You can read off what the mean of the Gaussian is, because in the Gaussian we have 2 times mu, the variable of interest times its mean. So this part here, if it's a Gaussian form, then this part here has to be the mean of that Gaussian. And, well, again, this we have the -1/2 sigma squared. So we have -1/2 sigma squared times mu squared, -1/2 sigma squared times mu, it's mean squared. This part has to be the variance of that Gaussian. Now, what do we know about Gaussian distributions that is very useful? Well, it's a distribution, so it's normalized. So this distribution, if we just write down a Gaussian distribution with this variance and this mean, will be normalized. And it will be equal to the posterior. And we completely got rid of the integration, the hard bit. That's why Gaussians are so nice and easy, because we can apply this trick very often. And we can just read off the coefficients of this new Gaussian. And, well, it's a normal distribution. For that reason, it's normalized. Well, let's take those means and those variances and rearrange a bit, and we'll see that the mean is now again this weighted average between the prior mean and the sample means. It's exactly the same mean as the map estimate, but we also get the variance in this case. And actually, in this case, it's easier to use 1 over the variance, which is the precision of a distribution. Think of so 1 over, whenever you hear precision of a Gaussian, that's 1 over the variance. And that is now again, this precision is now a weighted average between the prior mean and prior variance and the variance of the data. And these weightings are always weighted with n, proportional to the sample size. So if we observe more data, if n gets larger, then we'll be closer to the maximum likelihood estimator. And for small number of data points, we're closer to this. And so if n goes to infinite, the mean will be the maximum likelihood estimate, which for large amounts of data is very good. Actually, if the distribution of Gaussian, it will be exact in this case for an infinite amount of data. And the variance of the posterior will go to 0. What does it mean if the variance goes to 0? Well, if the variance goes to 0, then it basically means we have a distribution that has all its mass on a single point, and that point is the mean. So that means that we're absolutely certain about the identity of the parameter here. So if you observe enough data, then the prior doesn't matter. Only for small data sets, the prior doesn't matter at all. And well, this is demonstrated here. Say we have this prior and then observe some data sets. So we observe one data set, one point, then we observe a second point, 10 points. Gets more and more peaked. And goes to the mean of the data. Well, the time doesn't work. Do you have the time? 117? 317. Yeah, I would like to do a short drinking pause. I have a cold actually, so so that's why my voice is a little bit. Perfect, thanks. All right. Well, we saw that the posterior distribution was tractable in closed form for the Gaussian, being another Gaussian. The reason for that is that we use something which we call a conjugate prior. A conjugate prior is a prior for a particular likelihood where the posterior has the same functional form as the prior. So if you have a distribution and we choose a conjugate prior, then our posterior will again be of the same functional form. So if the prior is a Gaussian, the posterior will be a Gaussian. If the prior is, I don't know, some function, the posterior will be the function. Now, a conjugate prior might not necessarily be the best prior for a distribution. But it's usually the one that is easiest to use, and it's usually a sensible one. I mean, and, well, there's a large class of distributions, namely the so-called exponential family, which are written like that. And so it's basically, well, the distribution given the parameter is some function of the data times a function of the parameter. So these two are independent of each other, times an exponential function of the inner product of the parameter times some function of the data. And, well, the normal distribution, for example, falls into this category. For example, the Gaussian. In the way we typically see the Gaussian, this is not true, right? I mean, you cannot take the mean and the variance and write it into this form. But what we can do is we can find a different set of parameters and the function h, g, and u for which it will have this form. And that's what we do now. So basically, I think this is called the canonical parameter. And I'm not sure whether this is the sufficient statistic here. Or whether the sufficient, no, I think the sufficient statistic is everything that depends on x, which might be h of x times x of, I'm not completely sure. I can look that definition up. But the parameter is the so-called canonical parameter. And, well, if you rewrite the Gaussian and say choose, so basically the number of parameters will be the same as before. It will it's just some change of variables. So if we write down theta equals mu over the variance, mean over the variance, and minus 1 over 2 times the variance. And find some function h of x. See that h of x doesn't even depend on x, so it's some function h of x. A function u of x, which is x and x squared. And a function g of the parameter. Then we get back the Gaussian. Right? So if we just plug this all in, factorize it out, then we get the normal distribution back. If we plug in these for theta. It's just reorganizing things a bit. And, well, for all the members of the exponential family, it's possible to construct the conjugate prior. And this conjugate prior is also an exponential family. And both the posterior, the prior, as well as the joint distribution will be exponential families. And the conjugate prior for the Gaussian, well, for the mean, that's what we used, the normal distribution. The conjugate prior for the variance is actually a prior on the precision, not on the variance. So it's the precision, 1 over the variance, is distributed as a gamma distribution. We've seen the gamma distribution before. And, well, there's also a prior on, and basically the joint prior. So this is now the full conjugate prior over the normal distribution is the product over a normal and a Gaussian. It's what we call a normal gamma distribution. Normal and a gamma, not a normal and a Gaussian. So it's a normal gamma distribution. And right. And also the also the posterior, of course, is then also a normal gamma distribution, but with different parameters. Well, that was brought up before. Well, if you have independent samples, why not use the posterior as a prior? It's a good idea to do, and it's possible. So, say we get data sets. Well, D1 and DS. And these are independent data sets. They don't overlap. Never ever use your data twice. But what we can do is basically we can use the first data set times the prior to get the posterior. The posterior is again a normal distribution. So let's plug that posterior as and it's over the parameter. So let's plug that in as the new prior. And so on and so forth. And we've got a sequential learning algorithm. For example, if we get a sample one at a time, we could always just update the prior, or the posterior in this case, which is a nice thing because it's a way to compress the whole thing, right? I mean, we get the same answer, but we only need to keep the distribution over the mean and the distribution over the variance, and not all the samples that we've seen so far. You can discard them. Well, this is what I just said. Okay, let's get to linear regression. Say we're given a data set. The last data sets that we saw were just values of x. But now data sets are pairs of x's and y's. And, well, the x's have some certain dimensionality s, which means that each of the x's is a vector of length s. And, well, we want to fit some function f, which we call a regressor, as a function of the parameters. So we want to fit the parameters for this regressor f, for this function f, and Gaussian noise. This is the type of model. So basically y, for each sample y, is modeled as this function of x and the parameters and Gaussian noise. And the equivalent likelihood formulation is a Gaussian distribution, where now this function f appears in the mean of the Gaussian distribution. Is this concept clear, that we're now plugging in a function into this probability distribution? Instead of estimating the mean of this Gaussian, our goal is to estimate these parameters here. We can do that for different functional classes. And, well, the simplest one that we could choose is just a linear function, where our parameters, we call them beta now, are just will just be taken, and well, we'll just take the inner product of the data x and this parameter, and we might have some constant in addition to that, where we can actually drop the constant and without any loss of generality, because we can just, for every sample, we can just create an additional dimension for just an additional variable of x, which is just a 1. So I think we just take our x's, put a 1 in the end, and then have one more beta value, and basically our c is then in the beta value. For every individual will be multiplied by a 1, which gives c. Right? So that's the way to get rid of the offset. I mean, it's just it just helps me write less stuff on the slides, and if you code it, then it's a few lines of code less. Well, now this is kind of a graphical model representation of this. A graphical model, we've seen a simple graphical model in the beginning where we basically said this, we are doing an association study between genetics X and a phenotype Y, where we basically said these things are random variables, X and Y. Now we have some other things here pointing to those, which are in the Bayesian case, they're also random variables, right? I mean, basically, for Bayesian, we treat our parameters as random variables, and they the variance is in effect on y. Well, y is basically a function of x and those weights, and we have one of those. So everything that is just a dot will be there once, and these plates here are a way to replicate everything that's in a plate. So if we write down this sort of rectangle here, which we call a plate, with an n, it means that there are n x's and n y's, as many as we have data points. And well, some of these are observed, some of these are not observed. We observe something, we make it gray. So xn and yn are observed, so data, but the parameters are unknown. And those are white, and so we basically have to perform inference over everything that is not observed if you're in the Bayesian case. Well, let's start with maximum likelihood estimation, and that's actually for linear regression, that's something that we'll do most of the time. Write down the likelihood. Well, the likelihood, as you said, it's a Gaussian in y. So y is the part that we measure on. The mean is given by the axis and this linear function, and we have the variance of y. Basically, this variance measures now kind of this squared deviation of this linear function and y. Before it was the squared deviation of the mean and y, but the mean is now a function. So it's what we call the regression errors or residuals. But if you want to maximize, find parameters that maximize the likelihood, then the part that we need is again only this data term, which is the sum of squares. So the parameters beta that maximize the likelihood are exactly it's basically the linear function. It has the least sum of squares difference to y. So the likelihood is maximized when the squared error is minimized. That's a different sign here. That's why maximization becomes minimization. And this tells us that least squares regression, that's something that we've seen probably sometimes before, is exactly the same thing as maximum likelihood estimation in this probabilistic model. So it just is a different way to interpret it. And yeah, this is basically the error function, or kind of our the function that we want to. Is it already 41? Okay, so I'll quickly come to a good point where I can halt, and then so basically our objective now is the squared error. The objective that we want to minimize. We want to find the function that minimizes the squared error, squared distance to these y values. And to do so, we take again the derivative of the log likelihood. We can take it first with respect to a single parameter. And do you know how such a derivative would look like? This time there's nothing in shaded gray on the slide. Well, it's a sum, right? So everything that's the sum of squares. So we first have to take the derivative of the squares again, which basically leaves us with 2 times the part in here times the derivative of this, right? And the derivative of this is just, well, this inner product here is a sum. Is a sum over over all the entries in our parameter and the corresponding x values. And the derivative of that will just be that corresponding x value. Now, instead of taking just a derivative, we use a gradient. That's just easier. And the definition of a gradient is a very simple thing. It's just we take all the derivatives with respect to all the parameters and write them into a vector. And this gradient now, basically, well, before we said that the derivative is basically the inner part times 2 times the inner part divided by 2 again, so that 2 goes away, 1 over sigma squared, times the corresponding value in x. If we concatenate all those, we get all we get the complete x, basically, when we go from the derivative to the gradient. So in the derivative, we only have one dimension of x, so it would be a scalar. In the gradient, we can just take the whole vector. We set that to 0, and what's the solution of that? Well, I probably will do that next time. And you can think about it if you want. Actually, I have, so we'll stop here. I have prepared exercise sheets. Yay! Well, I mean, we just want to train a bit these computations here. So if just give it around.